Hey, G-Sauce!
Do you know what a supernova is? It's a big, large explosion.
Explosions!
Because a star collapses in on itself.
And it's weird because something this Brobdingnagian happens all the time.
And the most Brobdingnagian supernova ever recorded measured a whole 220 decillion kilowatts, which is 580 billion times brighter than the sun. And it also had enough power to power the planet for 2.8 billion years. But how'd it do?
To answer this, we need to look into the science and chemistry behind supernovae.
A star is born from nebula in space. That's essentially a giant cloud of hydrogen gas. Eventually the cloud accumulates enough gas to form a gravitational field, and the gas compresses under its own gravity. Eventually, when the pressure gets great enough, the hydrogen atoms fuse together to form helium. The fusion process produces heat, light, and also an outward force on the star that prevents gravity from compressing it even further. At this point, it's also called a main sequence star, or a stable star. The force of hydrogen fusion perfectly equals the force of gravity, and the star continues to burn gas. Eventually, though, the star runs out of hydrogen gas to fuse, and it starts fusing the leftover helium from the hydrogen. The fusing of helium forms carbon, and then when the star runs out of helium, it starts fusing carbon. The next element, then the next, and so on. As the elements get denser, the fusion force pushing out on the star gets greater and greater. In fact, the force gets greater than gravity, and it starts pushing outward on the star. The star begins to grow outward, anywhere from 100 to 1,000 times its original size. The growing stage is called a red giant, or a red supergiant based on its mass. It continues fusing heavier and heavier elements all the way until it gets to iron, the first element that's too heavy for the star to fuse. At this point, it runs out of fuel.
And finally, at the end of this star's life, comes the supernova, a high-mass explosion that comes from the star crumpling in on itself until it can't withstand its own gravity. After the supergiant runs out of nuclear fuel to power it, it has no outward pressure to balance the inward force of gravity. So the outer layers of the star collapse in onto the core and are dramatically expelled in a nuclear explosion at a velocity up to 30,000 kilometers per second, or 67,108,089 miles per hour, around 10% the speed of light. What remains of the core would either become a neutron star, or, if big enough, a black hole. A neutron star is the incredibly compact core that still remains after a supernova. The material is so compressed that the atoms have been smashed apart, leaving just neutrons. Once the supernova happens and everything goes boom, the supernova could leave a rapidly spinning neutron star behind, weighing as much as up to 2 suns, but only being around 20 kilometers across, or 12.4 miles wide. For reference, a house of neutron star-like material would have the same weight as our moon. Black holes are created when supergiants end their lifetime in the event of a supernova. Everything that's in the star is crushed down to an incredibly small, dense object. Close to the object, gravity is so strong that nothing can get away, not even light, giving these phenomena the nickname black hole. This black hole is created and sucks up a lot of things, then dies in a short amount of time with abrupt explosions of its mass.
Let's go.
This is our demonstration. The melon is acting as a star, and the rubber bands are acting as gravity pushing in on the star. Alright. God. Oh no.
Our original idea for the demonstration was to just put rubber bands around the watermelon and keep putting more and more on until it exploded. This, however, proved quite a challenge, as we kept putting more and more rubber bands on, and the watermelon showed absolutely no signs of stress. Finally, we decided to just drop the watermelon, which you will see in a bit. In this demonstration, the rubber bands act as the extreme heat and pressure that happens right before a supernova, and the force of it hitting the ground acts as just the last little push which causes the chain reaction.
our demonstration, this watermelon represents a star, and these rubber bands represent the gravity that's pushing in on the star because it ran out of fuel. So whenever that happens, eventually, supernova!
And now you know the chemistry behind supernova. Big, giant, Brobdingnagian stars that explode because they can't handle themselves.
But don't do anything zestful with this information.